encoding. So, welcome. So we're going to do circular motion notes. And basically we're going to do circular motion in part because the mathematics of uniform circular motion is very useful for doing things like vibrations and waves and electricity and light. But we're only concerned with the mechanical side of things at the moment, so we're talking about uniform circular motion. And that would be when you go in a circle at a uniform speed. And we have 4 classic examples of this. One is a so-called soap on a rope, which is a mass on the end of a piece of string, and you just swing it in a nice flat circle. And then the other is a conical pendulum, where you take the same mass and the same piece of string, but you don't make it into such a big circle. It kind of is a conic section. And then there's, imagine a car going around a flat racetrack. So it's a circular track, but there's no bankment on it. And then imagine the same car on a bank track. Those are the 4 applications of circular motion. And we're going to use Newton's second law, sum of the forces equals ma. But in this case, the A is going to be the A that's with circular motion, uniform circular motion. And where does this A come from? What we have is we have a object like a car which is going around a circular track. Got to get my pen. So I have my object going around a circular track, and at one instant its velocity is there, and at the other instant its velocity is there. So let me ask you, constant speed, of course, are those two the same velocities if that is a constant speed? What do you think? So what's the difference between velocity and speed? Yeah, both have magnitude, but velocity has direction. Are those the same direction? So not the same direction, not the same velocity. Oh, more significant than I thought. The velocity, the direction matters. Okay, so this is my final velocity, and that's my initial velocity. And if I think back about it, I said that my acceleration is equal to my change in velocity, which equals Vf minus Vi. Do you remember that from the first section that we did? So my final velocity, so how do I do this? I take my final velocity, which is that guy, and I add onto it Vf plus minus Vi. That's how we do vectors. So if the positive Vi is like that, the minus Vi is like that. So we add that minus Vi on. And we get a resultant. There's my Vf. I'm going to add on my negative Vi. And I get my delta V, which equals my change in velocity. Oh, I'm sorry, I cheated on that. Delta V over delta T. So my delta time is the time interval between when I took the second picture and when I took the first. So my AC is equal to my delta V over my delta T. But my delta V does exist. It's a vector. And which direction is it pointing to on this diagram? Center of the circle. So the centripetal, like petal of a flower, centripetal acceleration, like the petals of a flower, point to the middle. So centripetal acceleration points to the middle. And what's its size? Ah, that's a different question. Hopefully we do a lab. I can't remember when we do it. I don't think we do it today, but hopefully we do a lab, maybe after the test, in fact, when we'll actually figure out what the magnitude is. But we need to know it, and it is the velocity. Yeah. Really, this should be the speed squared. Because I only care about the magnitude. I don't care about the direction of the velocity. But often people say the velocity squared. We're our own worst enemy to some extent. We use language badly. But it's speed squared over the radius. Okay? Where does that come from? We'll figure it out in lab. For the moment, just know that that's the case. So what is the centripetal acceleration experienced by a 5 kilogram mass that moves 12 meters per second around a circle of 4 meters radius? So here's my 4 meters. And here's and that's going to be a 5 kilogram mass. And it's traveling with a speed, tangential speed, 12 meters per second, constantly around there. And we say, what do I know? M is equal to 5 kilograms. R is equal to 4 meters. Let's look. V, I'm going to call it V, its speed is equal to 12 meters per second. And I want to find my AC. And what I know is that my AC equals V squared over R, which equals 12 squared over 4, which equals 36. 144 divided by 4, which is 36 meters per second squared. And it is AC pointing towards the middle. Hold on! We didn't use our acceleration. We didn't use our mass. Yeah, we didn't need to use it. I asked you about the acceleration. Maybe another time I'll ask you about the force. I'm going to try not to. I try to avoid talking about centripetal force. It's not that it doesn't exist, but it is a bit confusing because the centripetal force is not caused because this object goes in a circle. What makes this object go in a circle is the tension in the string, which is the tension in the string. The centripetal force is the amount of tension force I need to cause this thing to go in a circle. So the tension in the string causes the acceleration, which causes the circular motion. How much tension in the string do you need? It's the mass times the acceleration. When we combine that mass and the acceleration and we start calling it centripetal force, if you're anything like me, you think, oh, there's a new force on there. Oh, we have a new force. And we start trying to factor that force into things as if it exists in its own right when it is a debt. Centripetal force is a thing you have to get from some other thing. Tension, gravitational pull, electrostatics. But the centripetal force is a debt. It's not a thing that's created by circular motion. It's the amount that's needed to cause circular motion. It's a bit like, you're going on holiday, you need holiday money. You don't get holiday money because you go on vacation. You don't arrive in Miami and somebody says, on vacation? Oh, here's your holiday money. It's like if you want to go on holiday, you earn your money and it is your job money, or it is your, loan money, or it is your, whatever money, borrowed money. And if you have that money, you can then go on vacation. You call it holiday money, but it came from somewhere else. And it's like that with centripetal force. It is the debt. It's the bill you get. You had a meal, here's $50. Why? Because that's the money for food. No, you owe $50. You don't get $50 because you had a meal. So you don't get centripetal force because you're going in a circle. It don't work like that. So you've got to be really careful of that. So over the years, I've started using centripetal force less and less. I talk about centripetal acceleration for sure, but I talk about centripetal force less and less because I'd see people with all the forces plus FC, and it's like, well, the tension gives the FC. Sometimes the tension does two jobs. it might supply a reaction force to weight and pay for the centripetal acceleration. Can be doing 2 or 3 things. So it gets confusing if we're not careful. A block or mass moves in a circle of radius r with tangential speed of v. What trace best represents the relationship between the block's centripetal acceleration and the tangential speed? So I want to say, what am I looking at here? I got mass is part of this thing, and r is part of this thing, and AC, of course, is part of this thing, and v is part of, oh yeah, AC equals v squared over r, yes? And I am plotting, so AC is equal to 1 over r times v squared. Now, when I'm plotting AC versus v tangential, I can't change anything else. You can't just change everything in the equation at once. That's not how graphs work. Graphs work by you change v and you say what happens to AC with everything else held constant. Otherwise, it's a meaningless exercise. So the 1 over r doesn't change. So some people can look at this and they can say, oh yeah, that's a, what's it called? It's a x squared relationship. What's that? Y equals x squared. What would that be? Parabola, yeah. It's a parabola. So you could say, oh yeah, it's going to be that, and they can just see it. And for others, it's not that case. So what do you do if it's not that case? Then you go AC, and you go V, and you say, I don't know what 1 over r is, but let's call it 1, because life is too hard. If 1 over r is 1, V is 1, V squared equals 1. If V equals 0, V squared equals 0 squared. If V equals 1, AC, which equals V squared, equals 1. In fact, it's probably better. I actually would recommend you do this. So this is 0 for V, 0 squared for V squared. That's 0 for AC, because 0 squared is 0. That is 1 squared, so that becomes 1. This is 2, this is where this pays off. This is 2 squared, which becomes 4. And this is 3 squared, becomes 9. But the fact is, you're plotting AC against V, not V squared. And so it goes 0 and 0, 1 and 1, 2 on 4, 3 on 9. Oh yeah, look at that. It's E. And in this, current test, if I ask you for the trace, you pick the trace out. Later on, I could ask you for the graph. Just give you a little grid. Say, you draw a graph for me. Put numbers down. I want to see what you do. Block moves in a circle. It has an acceleration of 9 meters per meter squared. What would the centripetal acceleration be of a new block if it had triple the mass and 4 times the velocity of the old? So we have this thing. There's our old. And then we have this thing. And there's our new. And let's have a look. I say, what is the relationship? I'm trying to relate AC, mass of the block m, 4 times the velocity v, r. Okay, so then I've got to think about my equation. AC, which is what I'm talking about, AC, is equal to v squared over r. Again, m is just there just to throw a wrench in the works. AC new over AC old is equal to AC new over, what was the AC old was 9. And that equaled V new squared over R new divided by V old squared over R old, which equals, and I say triple the mass. Mass is not in my equation, don't care. 4 times the velocity. So let's make the new one 4 and square it. Let's make the old one 1 and square it. And then it follows the path twice the radius. So make the new radius 2 and make the old radius 1. So that comes down to 4 4s are 16 over 2, which is 8. And a bunch of people will give me 8 meters per second squared for the answer, because they're not thinking in terms of the full equation. AC new over 9 is equal to 8. So AC new is equal to 8 times 9, which equals 72. 9 8 is 72 meters per second squared. So again, that same skill. It's picking the equation, putting the new over the old, putting the ratios in, working the math. It's very nice. If you lay it out, some people can do these in their head. Great. If you get the answer right, as long as there's some working, I'll give you credit for it. If you do it in your head and you get the answer wrong, you don't get anything for it. So use the method, it works. When you're stressed, when you're under duress, you'll get more of them right. Last thing we're going to do today. In uniform circular motion, a centripetal acceleration must always point towards the center of the circle. If you're moving in a circle, you have an acceleration towards the middle. If you're going slowly in a circle, you've got an acceleration towards the middle. It's little. If you're going quickly in a circle, you have an acceleration to the middle. It's big, but you always have an acceleration towards the middle. Centripetal acceleration must provide the force such as the tension, must be provided by a force such as the tension in the string, or the gravitational pull on the moon, or the electrostatic charge between the electrostatic force between the electrons and the positons and the protons. Got to be some physical thing that causes that force. The object is in equilibrium and thus will continue in a straight line. Oh, sorry, no. If the string is broken, then what happens? Conceptually, many people think that happens. You break the string, you fly out. And I remember on a roundabout, my brother gave me a nudge one time and I flew away from him. And it seemed like I flew out. But in reality, what happened was, here's my mass and here's my velocity. And so inertia says I continue in the same velocity unless there is a net external force. And once he has stopped my friction onto the table, I am flying through the air. There's no net external force in the plane of the room. So I travel in a straight line. And what happens is that as my brother as I go further and further away, I am looking at my brother, and it seems like I'm flying out away from here, but actually I'm following this direct line. You follow a linear path. So given the situation's geometry, the straight line is a tangent to the previous circular path. That's a bit of conceptual bit. You don't do that. Some people think you do that. Some people think you do that. They're all adding complexities. Resistance, air resistance one way, air resistance the other way. It's insignificant. You go in a straight line. Next time, we will apply these things. So this is where the mathematics comes in, and this is a bit of a lift. So I'm happy to leave that. But, we've got a few things here that I think are quite accessible. So I'm going to draw the line there. So if you want to write down 48H slide 9, 48H slide 9, we stopped at 48H slide 9. Anything to write this on? Because I sometimes forget as well, especially when I'm trying to write your test. So 40, it should be 49. Oh no, you're 48. 48H slide 9. That's the end. Let's look at the beginning. Let's get out of here. It was on vectors. And let's go to slideshow. And if I recall correctly, it was there, wasn't it? Or was it? It's there, isn't it? Yes? That is 48D20. Look through the old tests. They will help tell you which bits come up often and which bits don't come up so often. There's no guarantee, but if it comes up often, there's more of a chance it's going to come up. I try to ask lots of questions so that the important bits do come up often. You're going to get something on a traffic light, some kind of statics, traffic light or thing on a slope. You're going to get something, mass on a block or something accelerating. You may get a bit of both. You're going to get something. I'm going to give you something on centripetal acceleration. I just did it today, so I'm going to do something on that. Friction, there's going to be something on frictional forces. You can almost, I bet if you made a list of the 10 most important topics, and I made a list of the 10 most important topics, I bet there won't be that much difference between them. So just why not do that as an exercise? Pick out 10 things and say, I'm not going to give points upon these 10 things. It's like, I want to ask you important things. I want to